Good evening, everyone. Welcome to the week 4th of the tutorial session of the course Principles of Modern CDMA MIMO OFDM Wireless Communication System. I'm Abhishek Thakur, PMRF scholar from IIT Hyderabad. So we'll solve some of the questions based on the week 4 lecture of this course at NPTEL, and also this video will be recorded and will be uploaded on the YouTube. And also today we will see some of the concepts of week 3 and week 4. So before moving on to the questions, first we will see what we have studied in the last class, like the delay spread and the formulas of all the kind of delay spread. The first one we studied as a maximum delay spread. So this is known as the maximum delay spread. So maximum delay spread was basically the time duration between the last arriving component and the first arriving components. So this is tau of L minus 1 minus tau of 0. So tau L minus 1 is the last arriving component and tau 0 is the first arriving signal component. The second we studied as the mean, like average delay. So that is given as tau bar, average or mean delay. We have also derived all this in the last class on Saturday. So today I will directly write the formula. So this was given as summation of gi tau I divided by summation of gi. What is gi? That is the power of the ith component. So gi is basically mod of ai square. So this is the formula of average delay, that is tau bar. Now the third one we studied was the root mean squared RMS delay. So the formula of RMS delay was given as square root of summation of I is equal to 0 to L minus 1 gi tau I delays of the ith component minus average delay whole square divided by summation of ai mod of ai square. So we have studied three kind of delay. The maximum delay spread, that was the delay between the last arriving component minus the first arriving component. Second was the average delay, and the third average delay was weighted with the power of each signal component. That term is GI, that is the mod of AI squared. And the third one was the root mean square delay spread. So these three we have studied, and we have also solved one question. Now we can take one example and solve it. The power profile, find the so power profile is given here. L is equal to 4. So at t is equal to 0 microsecond, this was minus 20 dB, and t is equal to 1 microsecond, the signal component arrived was at minus 10 dB. T is equal to 3 microsecond, the signal component arrived was at 0 dB. And t is equal to 5 microsecond, the signal component arrived was having the power of minus 10 dB. So this is the power profile given for L is equal to 4 multipath component. We have to find the average delay and the root mean square delay, and also we can find the maximum delay spread. So the first one, we can easily find maximum delay spread, that is tau of 3 minus tau of 0, that is equal to 5 microsecond minus 0 microsecond. This is equal to 5 microsecond. The second one was tau bar. So the formula is summation of gi ti divided by summation of gi tau I. So this is the formula, but here gi is given in dB, so we have to convert that into the normal unit. So let's make a table. At t is equal to 0 microsecond, 1 microsecond, 3 microsecond, 5 microsecond. The gain in dB was given as minus 20 dB, minus 10 dB, 0 dB, and again minus 10 dB. So the value of G will be, and here we'll also find the value of A. So 10 log 10 G is equal to minus 20 dB. So the value of G will be 10 to the power of minus 2, that will be 0.01. So basically GI is the mod of AI square. So AI will be under root of GI. So A will be here 0.1, square root of G. Again for minus 10 dB G is equal to 0.1 and A will be a square root of that, so that will be 0.3162. Now for gain 0 dB G will be 10 to the power of 0, that is 1, and a square root of 1 is also 1. Again for minus 10 dB we have already calculated 0.1 and 0.3162. So this is a tabular representation of all the signal component. Now tau bar is equal to summation of gi tau I. So for I is equal to 0, the value of gi is 0.01 and time is 0, plus 0.1 into 1 plus 1 into 3 plus 0.1 into 5 divided by power of all the components 0.01 plus 0.1 plus 1 plus 0.1, and the unit will be in the microsecond because time is in microsecond. So tau bar is equal to 3.6 divided by 1.21 microsecond, so that is equal to 2.9752 microsecond. So this is the average delay. Now coming to the next question, that is the root mean square delay. So the formula is summation of gi tau I minus tau bar square divided by summation of gi, and whole is the square root of this. So we can expand this and calculate. So after expansion G naught is 0.01, tau I is 0 microsecond, and mean tau bar will be 2.9752 and whole square, plus the second is 0.1, the tau I is 1 microsecond, 1 minus 2.9752 micros whole square. The third one is 1, the gi is 1, time is 3 microsecond, so 1 into 3 minus 2.9752 square. The fourth one, the power is 0.1, time is 5, divided by summation of all the gi. So that is 0.01 plus 0.1 plus 1 plus 0.1, and the square root of this complete term. So when we do this calculation, we will get 1.059 divided by 1 point, after calculating we will finally get 1.121 divided by, I can write directly the answer for this. So it will be, or we can calculate also, 0.01 into 2.97 into 2.97. The first term will be a square root of 0.088 plus 0.388 plus 0.0009. 0.4120 divided by 1.21. So final answer we will get around 0.87 microsecond. So we can see that RMS delay spread is much smaller than maximum delay spread. The value is 0.87 microsecond, here 5 microsecond. So where this is useful, like there are the signal components which is having very low power but arriving later with a delay. So those signal component can be removed using this. And also the delay spread have a very important impact on the like signal, like it also determine the inter symbol interference that we will see. But before that, let's start our first question of today's lecture. So when symbol time is much larger than the delay spread, the resulting wireless channel is flat fading. So when symbol time is much larger than the delay spread, the resulting wireless channel does not have inter symbol interference. Hence, the resulting wireless channel is flat fading in nature. So we will see this. We'll first go through the concept of this topic. Like inter symbol interference occurs when delay spread is greater than the time period of a symbol. So this is the case for inter-symbol interference. So to avoid ISI, the time spread of the symbol should be greater than the delay spread. So that is, so this implies that if symbol time is less than the delay spread, then there is the ISI, and when the symbol time is greater than delay spread, then there is no ISI. Why this is like this? Let's suppose this is our S0, S1, S2, S3, S4 and S5. And this is the delay, like this is the time period. Now let's suppose the delay spread is greater than the time period of the symbol, like it start occurring here. This is our S0, S1, S2, S3, S4, sorry, S0, S1, S2, S3, S4, S5. So if this T is greater than the symbol spread, like symbol spread is greater than the delay spread, then there will be no ISI. Because in this case you can see that sigma tau is greater than T. So when you combine these two, there will be the inter-symbol interference. Now let's suppose the symbol have a bandwidth of Bs. This is the bandwidth of the symbol that is given as Bs, and the channel have the bandwidth of Bc. So this is HF channel bandwidth and this is the signal bandwidth, like the XF. Now the received symbol YF will be XF into HF. So when there will be no distortion, when this part, this BC part is greater than this BS, then there will be no distortion. Okay, so if BC is greater than BS, then there will be no distortion. So this is known as the flat fading, and the received symbol is the similar to the uh, transmitted symbol, that is X. So this is the case of flat fading. Okay, so if coherence bandwidth is greater than, and this BC is known as the coherence bandwidth, symbol bandwidth, like this coherence bandwidth is greater than the symbol bandwidth, then there will be the flat fading. So our first question is based on this only. So when symbol time is much larger than the delay spread, then the resulting wireless channel is the flat fading. Also, let's take an example, like each cell in a wireless communication system have a radius of around, let's suppose this is a one cell in the wireless system, and the radius of the cell is in the range of kilometer. Therefore, line of sight and null line of sight signal is also in the kilometer. And delta D, let's suppose this is our tower and this is a user. So there is some line of sight component and there is some null line of sight component. So delta D, the difference in distance between the will be in the range of kilometer. So the delay spread sigma tau can be calculated as delta D by C, that is the speed of light. So let's suppose this is 1 kilometer. So we will get this in a microsecond. So delay spread is equivalent to 1 to 3 microsecond. So if the symbol bandwidth is less than the delay spread, then there will be ISI, as we have already studied here, these two cases. And when the symbol time is greater than the delay spread, then there will be no ISI. And we have also studied about coherence bandwidth. But in coherence bandwidth, there will be a case, like in this case what we have studied, when the symbol bandwidth is less than the bandwidth of the channel, then the received signal is the transmitted signal. But what if the bandwidth of the channel is less than the bandwidth of the symbol? Like let's suppose xt is transmitted through a channel and yt is the received signal. So yt is just xt convolution ht. In frequency domain we can write yf is equal to convolution in time domain changes to multiplication in the frequency domain. So this is we can write. Now let's take an example. This is our symbol having bandwidth of bs. The next is the channel bandwidth. Let's suppose this is our bc. Now the final one is the received symbol. So this will now this time changes, and from bc it won't be exactly the transmitted symbol xf. So this value will change this time, and yf is equal to xf into hf. So the distortion is there. So the distortion is there due to the channel bandwidth is less than the symbol bandwidth. So symbol bandwidth is greater than the channel bandwidth. So this is known as frequency selective. The previous one was the flat fading. So now we'll move on to the question number 2. Or before that we will study about the coherence time formula also. So in frequency selective distortion, so this is a frequency selective distortion. So in this, BS is greater than BC. So BS we can write the bandwidth is in the frequency, so that we can write as a reciprocal of time, that is 1 by time is greater than 1 by symbol spread. This implies that symbol spread is greater than the time duration of the symbol. So it's implied that the ISI will occur. Okay. But in the flat fading, there will be no ISI because 1 by sigma tau is greater than 1 by T. So T is greater than sigma tau. So there is no ISI. Now we will see the Doppler effect. Like the equation for the fading coefficient of the channel is given as H is equal to summation of AI e to the power of minus j 2 pi fc tau y I is equal to 0 L minus 1. But when the mobile user is moving, then there will be a Doppler shift. Okay. So when a mobile device is moving, then Fr is equal to Fc plus Fd. So this is our received frequency, that is equal to carrier frequency plus the Doppler shift. Now due to that, the equation of the fading coefficient will change, and we can write Fc is equal to Fr minus Fd. Okay. Now let's suppose this is our base station and here is the user. The angle between the base station and the user is, let's suppose, a theta degree, and user is moving towards this direction with the velocity v. So if user moving towards base station, the distance will decrease and the delay tau y will change. Okay. So now what will be the equation of tau y, the equation of delay with respect to time? So this will be tau y minus v cos theta by c into t. So now we will substitute this in the equation of the fading coefficient. So we will get h is equal to summation of ai e to the power of minus j 2 pi fc tau y minus v cos theta t divided by c. So finally we can write it as ai e to the power of minus j 2 pi fc tau I into e to the power of minus j 2 pi fc v cos theta c into t. Now this term we can write as fd. Okay, so that is the Doppler frequency. Therefore, like the equation is of the channel coefficient h is time varying now. So at t is equal to 0, this term will become e to the power of 0. So there will be no shift in the phase. So phase shift is equal to 0. At t is equal to 1 by 4 of fd. So this term will become pi by 2 e to the power of minus j 2 pi by 4. So it will become pi by 2. So the phase will be pi by 2. So the coherence time is equal to 1 by 4 fd. So coherence time is tc and fd is the Doppler frequency. So option D is the correct answer for this question. Now coming to the question number 3. Consider a channel with coherence bandwidth of 700 kilohertz. The delay spread of this channel is equal to. So the delay spread will be 1 by coherence bandwidth. So this will be 1 by 700 into 10 to the power of 3 second. So that is equal to 1 by 7, 10 by 7 into 10 to the power of minus 6 second. So we can write as 1.4 microsecond. So the correct answer is option A. So now we'll move on to the next question. The frequency selective fading in wireless channel leads to. So it leads to inter-symbol inference. We have already studied here that frequency selective distortion leads to the inter-symbol interference. Why? Because the symbol bandwidth is greater than the channel bandwidth, so the signal is not reconstructed properly at the receiver end. Now coming to the question number 5. Consider a wireless system with carrier frequency fc is equal to 3 gigahertz, and for independent fading across L is equal to 8 antennas. What is the minimum length of the device? So dmin is equal to lambda by 2. We have studied this formula. So lambda is equal to c by f. It will become c by 2 into fc. The speed of light is 3 into 10 to the power 8 meter per second, and carrier frequency is 3 gigahertz. So that is equal to 2 into 3 into 10 to the power of 9. So it will be 0.05. So that is equal to 5 centimeters. Now here is the L antenna. L is equal to 8 antenna. So there are 8 antennas. So minimum size of device is equal to 7 into 5, 35 centimeter. So option B is the correct answer for this question. Now moving on to the question number 6. Let's consider a wireless system with carrier frequency 1.5 gigahertz for independent fading across L is equal to 6 antennas. What is the minimum length of the device? So it is the same question. Here FC is equal to 1.5 gigahertz. So this can be written as 1.5 into 10 to the power of 9 per second. So that is hertz. Number of antenna L is equal to 6. So minimum length of device is equal to 5 into d min. So 5 into lambda by 2. So lambda we can write C by F. So the final answer will be 5 into 3 into 10 to the power of 8 divided by 2 into 1.5 into 10 to the power of 9. So this will be 1 by 2 is equal to 0.5, that is 50 centimeter will be the answer. So option D is the correct answer for this question. Coming to the question 7th, frequency selective distortion occurs in a wireless channel when? This we have already studied. It occurs when the signal bandwidth Bs is less than the coherence bandwidth Bc. When Bs is greater than Bc, like coherence bandwidth is less than the signal bandwidth. So coherence bandwidth is lower than the signal bandwidth. So option B is the correct answer for this question. And when this happens, then it's a distortion occur, due to which leads to ISI, intersymbol interference. Now we will see some concepts of now we little studied about the concept of Doppler shift. So this Doppler effect occurs when the like user node or receiver node or mobile is moving. User is in motion. So this occurs when user node is in motion. And due to this, it leads to change the frequency received at mobile node. Okay, so this is the Doppler effect, and this occurs due to motion between transmitter and receiver. Now, calculation of Doppler. Let's suppose this is our base station, and here is a mobile node which is moving. So the angle between the mobile node and the base station is, let's suppose, theta, and node is moving with velocity v. And angle between moving mobile node and base station is theta. So the Doppler shift FD is V cos theta by C into FC. So this is very important formula. V is the velocity of the mobile node and theta is the angle by which the node is moving, the angle between the transmitter and the mobile user node. And this concept is also used in radar to track the velocity of the obstacle. And FC is the carrier frequency. So the received frequency is carrier frequency plus the Doppler frequency. So we can write the formula Fc plus V cos theta Fc by C. You can take Fc common also, 1 plus D by C cos theta. Now if theta is between 0 to pi by 2, then mobile is moving towards base station. In that case Fr is equal to Fc plus V cos theta Fc by C. So this term will be a positive value. So therefore receive frequency is greater than or equal to the carrier frequency. Now in the second case, if theta is greater than pi by 2 and less than equal to pi, then cos theta is less than 0. So the received frequency is Fc plus V cos theta Fc by C. Now this term will be negative. So Fr is less than Fc. So in this case, mobile is moving away from the base station. Also we can see, like, let's suppose this is our base station and this is our user node. Now if this is moving away from the base station, then angle will be here, you can see this theta will be greater than pi by 2 and less than pi. Okay, so in this case the mobile is moving away from the base station. So now let's solve the question. Consider a mobile user moving with velocity 90 kilometer per hour, kilometer per hour at carrier frequency of 2.5 gigahertz and an angle of 45 degree. So velocity is 90 kilometer per hour. So we can change into meter per second. So it will be 25 meter per second. And the coherence time we have to find Tc, that is equal to 1 by 4 of Doppler frequency, but the Doppler frequency Fd is equal to V cos theta by C into Fc, what we have studied just now. So we'll substitute all the value. 25, theta is here 45 degree, so cos of 45, Fc is 2.5 into 10 to the power of 9 hertz, 2.5 gigahertz, divided by speed of light is 3 into 10 to the power of 8 meters per second. So this is equal to 25, cos 45 degree will be 1 by root 2, six 25 is 62.5 by 3 root 2. No, 625, because there will be one 10 also. So 625 by 3 root 2. So this is equal to 147.31. Now the coherence time is 1 by 4 FD. So this is equal to 1 by 4 into 147.31 second. So this value will be 1.7 into 10 to the power of minus 3 second. That is equal to 1.7 millisecond. So correct answer is option number D. Now moving on to the ninth question. The coherence bandwidth of a wireless channel is approximately equal to. So that is approximately equal to the delay spread. So the coherence bandwidth is approximately equal to the delay spread. So like reciprocal of delay spread, that is 1 by TD. So option A is the correct answer for this question. Now moving to the last question. The time selective fading in a wireless channel leads to. It leads to the time varying channel. The As we have studied here, the angle between the user and base station changes with respect to the time, and we have also studied the equation for that. Here we have studied. Now we'll solve one last question. for today's lecture. Consider carrier frequency is equal to 1.85 gigahertz and the vehicle moving at 60 miles per hour with towards the base station at theta is equal to 30 degree, then find what is Doppler shift and what is the received frequency. So now for finding, we'll first change the velocity 60 mile per hour into meter per seconds. So this will be kilometer per hour. So this will be 3 5 80 by 3 meter per second. Now we know that Doppler shift FD is equal to V cos theta by C into FC. So after substituting all this value, we will get 80 by 3. Cos 30 degree will be root 3 by 2 divided by 3 into 10 to the power of 8, and FC is 1.85 into 10 to the power of 9. So after calculating, we will get FD is equal to 143 Hertz. So this was the Doppler shift. Now the second is the received frequency. So received frequency is the carrier frequency plus the Doppler shift. So this is equal to 1.85 into 10 to the power of 9 Hertz plus 143 Hertz. So this is nearly equal to the same carrier frequency. It's a very minute change. So today we will end the lecture here only. If you have any doubt, you can ask. And tomorrow we will not tomorrow, on Saturday we will have again the lecture at 3 to 5 p.m. and from next week we will have only one lecture, that is from Tuesday 6 to 8. So thank you everyone for attending, and this video will be recorded and uploaded on YouTube. The link will be shared in the NPTEL portal. If you have any doubt later on, then also you can ask in the YouTube comment section or even on the NPTEL portal too. Thank you everyone. So we'll close the lecture here only now. So if anyone have doubt, can ask. Okay, thank you. So we'll meet on Saturday 3 to 5 p.m.